Okay, my friends, so here is going to be an example of what's called a Monte Carlo simulation. And what that basically means is I can't find anybody online that will give me a solid concrete answer about how skewed can data be until you can't trust it anymore. So what I've done is I've created a simulator that generates bell curved data, and what I'm going to do is I'm going to move this histogram down here. There it is. It's hidden in there. So these points right here utilize a command called normin. You don't have to know this, but what it does is it generates randomly distributed bell-shaped data, and that's what the little rand command in there means. And I've got 14 of them because I have 14 eggs in my sample that we're analyzing on this quiz. So what this is right here is just a histogram of those. Now that looks pretty bell curved. I mean, as far as what we've been looking at in class, it's a little bit skewed, which you can see down here. You see how it's got a little bit of a positive skew, but that skew is very close to zero. A little bit of a positive skew means it's skewed to the right. That means it's got a little tail over here. The kurtosis is a measure of the fat tail-edness. So the kurtosis is actually very close to zero as well, which means this data right here, if we were looking at data like this, we would not argue at all that it was not bell-shaped. We'd simply say that it was. But if I re-randomize the data, let's get 14 different data points. Okay, now it looks like this, and you'll notice the skew values and their kurtosis values change. And if I re-randomize it again, oh, look at that thing. It's got the U shape to it. It's wild. It's got the very fat tails, which you can see in the kurtosis measure right there. You've got some fat tails, and you've got, it's very symmetric. You can see that by the skew right there, that negative 0.067. That's very close to zero, which means it's symmetric. But now you see also the need for the kurtosis, because the kurtosis talks about, is it actually shaped like a bell? There are lots of things that are symmetric, but not everything is a bell shape. So I can sit here and I can generate data all day long. And you got to remember something. These are all bell-shaped data values. I mean, I'm generating these from a normal distribution. So if I pull this back up here, I can continue, and some, as you're seeing, are definitely more normal looking than others. Now, here's where we run into trouble. What does it mean? That's a fun one. What does it mean to be too skewed? Well, what I'm doing right now, as I'm generating these data points right here, I'm also keeping track over here of those kurtosis and skew values that we were getting on the left side. Now, it's a little bit of a cumbersome spreadsheet to look at. All the big work is happening behind these graphs. But you'll notice that every time I generate new data, these graphs are updating. So what I'm going to do is I'm going to let this graph update for, well, let's see. I just got to work. It's 7 o'clock. I think I'm going to do is I'm going to put a stapler down on this F9 button and then go to class. Get cleaned up for my commute, go to class, come back in a couple hours, and let's see what this thing looks like. And then we can interpret the results that we got. Okay, my friends, so it's still running as I speak right now. I love it because, well, I love it for a number of reasons, not the least of which is the fact that we've got these two beautiful curves for the cumulative kurtosis and skew, but also the histogram over here can't even keep up with the number of refreshes here. It's pretty ridiculous. Looks like I've gotten about, let's see, what's the sum of that? I don't even know what the sum of that is. Oh, I got to look at the wrong column. Hang on. I've got about 190,000 trials in. I think that's enough to call it good. So what you're seeing is you're seeing the distribution of all possible values of the skew and their kurtosis as these samples vary. So what I'm thinking we do with this, dear friends, is we establish believable ranges for the skew and their kurtosis, because that's what the whole point of it is, right? The point of this is how skewed is too skewed. And if it's okay on the skew, is it the right shape? That's what these numbers are telling us. So let's take a look. I'm going to look at the I'll look at the skew first. I need to move these graphs out of the way. So now I don't, this is not the cleanest spreadsheet. I'm going to clean this up for later use. But what you'll see is, what you're looking at in this graph, this skew graph down here, is you're looking at this column right here, which is the cumulative skew percentages. So don't worry about really what you're looking at other than that adds up to 100%. So this is 100% of all possible skew values. You can see that more of them happen towards the middle and few happen off the sides. So what I'm going to do is I'm going to highlight until I get about 2.5%, and it's right about somewhere between there and there. Somewhere between there and there. So I'm going to call that negative 1.3, and I'm going to do the exact same thing here until I get about that same percent, and it is right about, yep, right about 1.3. So in other words, 95% of all skew values, 95% of all skew values that are gotten from randomly distributed data are between a value of negative 1.3 and 1.3. So one interpretation we can do for that, dear friends, is if our skew value is between, if our skew value is between, I don't know what the hell I'm doing with this graph. I'm trying to make the graph smaller, and there we go. I'm going to try to say that whole thing again. 95% of the time, skew values from normal distributions are between negative 1.3 and 1.3, which means if we get a skew value from our sample that is between those two numbers, negative 1.3 and 1.3, we can assume that that's okay. It's not too skewed. This only applies to a sample of size 14. But in a sample of size 14, if our skew value is between negative 1.3 and 1.3, then it's not too skewed. We can do the same thing for the kurtosis. The kurtosis is a little bit more fun, I think, because it itself isn't a symmetric distribution. But that's okay. We can just do the same 2.5 off either end bit. So I'll do that over here. All right, so we start at the bottom, and we add up. Let's get to, that's 1%. Why aren't these percentages? That bugs me. Let's change into percents. Okay, now I'm happy. Let's give it some more decimals too. Okay. Okay, 2.2, 3.9. Okay, it jumped right there. 2.2 to 3.9. So we're going to look at, I'm going to call that negative 1.5. That looks like the dividing line, negative 1.5. On the other end, let's see what it is. Looks like it's at 1.8. That's 2.62%. It's pretty close, and the divider there is 1.8. So for kurtosis, if the kurtosis is between negative 1.5 and 1.8, that means that the curve we're looking at has the correct sized tails. So if the skew is okay, that means it's symmetric enough. And if the kurtosis is okay, that means the tails are okay. And put both of those things together, it means that we've got ourselves a good bell-shaped distribution. Let's go back to your quiz and see if our data meets those criteria.